You know, some of the most powerful, most creative generative AI in the world is locked behind this massive computational wall. It's so big, it's been practically unusable. Well, until now.
And the key to unlocking it, it's not a bigger supercomputer. Nope, it's a fundamentally different way of computing altogether. So let's break this down.
What we're talking about here is a really special class of generative AI called energy-based models, or EBMs for short. Now, these are not your everyday run-of-the-mill models. They have some truly unique capabilities that researchers have been dying to tap into for years.
So how do they actually work? Well, I want you to imagine a 3D landscape, with mountains and valleys. EVMs learn to shape this landscape so that any realistic data, like say a perfect photo of a cat, sits way down at the bottom of a deep, low-energy valley. But unrealistic data, like a cat with 3 eyes, gets shoved way up on top of a high-energy mountain peak. The entire job of the model is just to learn the right shape of this energy landscape for whatever data you give it.
So, why should we care about these EBMs? What's the big deal? Well, because, at least in theory, they are a superior form of generative AI. They can achieve state-of-the-art results, they're much tougher against adversarial attacks, and they just have a more, nuanced understanding of the data.
Okay, so if they're so great, why aren't we using them for everything? Well, this brings us to the villain of our story, this huge computational bottleneck that makes training and using EBMs, well, incredibly difficult. And at the heart of this problem is a process called Gibbs sampling. See, to generate a new realistic image, the model has to find one of those low-energy valleys. This is absolutely crucial, not just for creating new stuff, but for the training process itself. The model has to constantly compare what it generates to real data in order to learn.
The classical way of doing this is a method called Langevin dynamics, and it really shows you the problem. It's basically like dropping a marble at some random spot on our 3D map and just waiting. The marble slowly, randomly rolls downhill, nudged by these tiny forces until it eventually settles in a valley. And you have to repeat this process thousands and thousands of times for every single sample you want to generate. It is painfully slow.
The researchers behind the paper we're looking at today, they do not mince words. They call this process extremely computationally expensive and numerically unstable, even when you're using the best GPUs on the market. So the key here is this isn't just slow, it's fundamentally broken for complex problems. And just how slow are we talking? Well, in a lot of cases, the time it takes to find a valley can scale exponentially with how complex the landscape is. That little e basically means that as the mountains get higher and the valleys get deeper, the problem gets exponentially harder really fast. It quickly becomes impossible for even the best supercomputers we have.
But what if you didn't have to simulate that marble rolling downhill? What if you could just solve for the location of all the valleys all at once? This is where our hero arrives on the scene, the quantum computer.
And right here, you can really see the night and day difference. The classical approach simulates a physical process, step by painstaking step. The quantum approach just solves the single mathematical equation that governs that entire process. It's the difference between dropping thousands of marbles one by one and waiting versus just having a complete topographical map that shows you where all the lowest points are from the very beginning.
And the magic tool, the secret sauce that makes this topographical map possible, is a cornerstone of quantum computing called the quantum Fourier transform. It lets the computer analyze the entire landscape at once in a way that is just flat out impossible for classical machines.
So, we've gone from a slow, clunky simulation to a direct, elegant solution. That sounds amazing in theory, but what does it actually mean for performance?
Let's put some numbers to this, right? How much faster is this quantum shortcut really?
This table right here tells the whole story. Just look at that last column. It shows how the cost, the amount of work you have to do, changes as you demand more precision. That's the little epsilon symbol. For the classical method, the cost gets way worse, fast. If you want 10 times more precision, it costs 100 times more work. Now look at the quantum algorithm. The cost grows logarithmically. That means to get 10 times more precision, the work barely increases at all. It's an absolutely massive difference.
So the bottom line is this. The quantum algorithm gives you an exponential advantage in precision. It can find those low-energy valleys with a level of accuracy that would be computationally impossible for any classical machine, period. Now, this is a huge speed-up on paper.
And to be totally clear, the kind of large-scale, fault-tolerant quantum computers we'd need to really run this, they don't exist yet. But what this research does is give us a concrete blueprint. It moves these powerful EBMs from the realm of pure theory and brings them a whole lot closer to practical reality.
And you can see the potential right here. These are charts from the paper showing the algorithm in action. Even on the early quantum hardware we have today, the approach successfully rebuilds these complex functions with really high accuracy. It proves that the topographical map it creates is a faithful, accurate picture of reality.
The implications of this are just huge. We are talking about unlocking an entire class of AI that was basically out of reach before. This could lead to way more robust, reliable, and powerful AI systems down the line. And it kind of hints at a future where the most important AI work isn't done in massive data centers, but in specialized quantum labs.
And all of this leaves us with a really fascinating question to chew on. For the last decade, we've kind of assumed that the path to better AI was just more data and bigger models. But maybe, just maybe, the next true revolution in artificial intelligence won't come from a bigger classical computer, but from a completely new one.